I'm introducing Mahesh Patel. He has a very long bio. He's done a lot, so I pared it down quite a bit. Mahesh has 35 years experience in structural analysis and optimization across multiple disciplines in the aerospace industry, including aerospace, space, defense, as well as automotive and some other consumer goods. He's held leadership roles as engineering manager, crash and safety manager, and analysis team lead. He has expertise in nonlinear dynamic analysis, crash safety, structural optimization, and simulation-driven design. He's led analysis for Boeing commercial crew. He's optimized landing performance to reduce astronaut injury risk. Has received the NASA NESC award for his work on the crew module landing water methods. Actually worked that as well. I had the pleasure of working with Mahesh on the X-59 program, which he will be discussing today. And I can tell you from experience, he's a very talented stress analyst and a good team member. So without further ado, Mahesh Patel.
Hi, good morning, everyone. Thanks very much, James, for those kind words. Also, thank you to Craig and Yvonne for allowing me to present this. As a team, we did this project, which wasn't just me. So I do want to give some credits to Bill Ginetti, who is at the back. He is here today as well. It was just Bill and I who did most of the work using Hypersizer, but also credits to Gene, Jason, and Scott at Skunkworks, Lockheed. They were just tremendous. When we asked for information, they gave it to us. So that was really one of the key aspects of the whole project working well is when an OEM or a prime is that interacting with you to give you the information you need, you can get your work done really fast. I think most of you can probably been in similar situations where the prime just takes months to get back to you on information. These guys are really good, really fast. So today I'm going to discuss a little bit, go over how we use Hypersizer on the X-59 nose cone. We also did the inlet duct, but that's not in this presentation. It was just a nose cone, and how Collier Group really helped us hit our deadline. The thing we were really against here was time. We didn't have a lot of time. We only had, at max, about 8 weeks to get all the analysis done. Okay, so I'll just talk a little bit about what I'm going to present today. It's just some contents of what's coming up. So who is Swift? Most of you probably don't know who Swift Engineering is, so I'll go a little bit into that. What was the design criteria for the nose cone? Loads and the FEM model. Analysis and sizing, how we did that, and that's really the key of this whole presentation is using Hypersizer and how we managed to get all of the work done within the time, as I mentioned, was time critical. A little bit of testing correlation. We weren't really in charge of testing. That was Lockheed, but they did give us the test data that we could tie it back to our models and show good correlation. They also had our models, so they also did correlation using our models. And then just some last minute, ending conclusions. All right, so this is showing a different slide here. Okay, I'll just go off. Okay, a little bit about Swift, who Swift is. It's a quite an old establishment based in San Clemente. The owner was an ex-race car driver, so they started in racing. They used to make all the Atlantic Formula cars, design and build at Swift. Since then, they kind of moved into aerospace, as you can see all their projects. The one in the red box is obviously the one we're here to talk about, but they do other stuff. They also have some of their drones, their own technology. And they also license some of that technology as well to different countries and different OEMs, primes. As you can see, it's not a big company by any means. It's a small company, but they do some wonderful stuff, and they have some of the best composite guys manufacturing that I've ever come across. But they're not really well known, so hopefully you guys can look them up. I'm not with Swift anymore. I used to be with them, so this presentation is like X-Swift. So what is the X-59? So it's basically designed to reduce the sonic boom, so they're allowed to fly over land. At the moment, commercial flights are not allowed to fly over land because it makes a quite a loud boom. And so this is a flight demonstrator by NASA to basically measure the signature on land as they fly it across the U.S. and show that they can get about 75 perceived decibel level, which is almost like slamming closing a car door. So it's going to be very, very low boom. And the technology is in the shape and how they dissipate that sonic boom. There are some of the specs, as you can see, of the aircraft. The nose cone, as you can see, it's abnormal compared to any other aircraft, and it's almost half or a third of the aircraft. And that's the bit we had to analyze and reduce mass. So they basically came to Swift and said, hey, can you design, substantiate, and manufacture this nose cone? And there was some history with Lockheed and Swift, so that's why they came to us. And also, some of the criteria that they wanted to maintain was sort of make sure the shape of the nose stayed as expected at cruise. And they wanted to use the CAE or FEA analysis to basically substantiate so they can certify to fly over land. They're only making one of these, and they don't have a test article to basically go ahead and do some testing. So the analysis was going to be their main pathway to certification. And for that, they needed to write a substantiation report, a detailed report, just stress report, which people can use to basically verify the aircraft is worthy for flight. So the challenge was really they came to us and they had done some preliminary sizing on the nose, and the challenge was they were a little bit overweight. I believe they were north of 400, and based on their initial sizing, they came to us and said, hey, we're a little bit over budget of mass. Can you try to get it down? What can you do? So we kind of explained how our approach was going to be, and they wanted to get it down to about 350. That was their target. Every bit of mass at the nose really has an adverse effect on the rest of the aircraft because of the mass, the static moment it creates by having mass way up at the front. So that was one of the reasons, and also just overall aircraft weight wasn't within their budget. So one of the main thing was to take mass out. I'm sure they could have done it as well, but they also didn't have the time, and they were not really set up for this kind of work. They're more set up for, more of the productionizing their technology rather than one-off prototypes. So here's here's a criteria they gave us. It's got to do all these things and take mass out. As usual, it's always do all these things plus, by the way, make it half the weight or whatever they come up with. So some of the criteria, I'm not going to read through all of these, but they wanted to make sure this aircraft had about, I believe it's about 1,000 hours of service life. So it's only a demonstrator. It's not a long-term flying thing they're going to keep flying. They literally wanted to just fly it a few times, measure the signatures on the ground, and basically declare that this shape is good for supersonic flight that produces low shock. So let me just sort of walk through some of the steps of what we got, how we kind of approached this whole problem. So we get the G-frame from Lockheed, which is the image on the left. We created a detailed DFM of the nose. We attach that back onto the main aircraft of the GFAM, and basically we're planning to run some sizing. So at this point, I'll point out that I've never used hypersizer before this project. I was like an OptiStrut guy. All my optimization was done inside of OptiStrut. Before this, I'd heard of hypersizer for a long time, but never really opened it up or looked at exactly what it did. And I was a little bit, I wasn't sure because it's something new and I didn't have time to learn. And I was used to one tool for such a long time. It's kind of like afraid to move to a new tool. But Bill and James, basically, you know, their support really started sort of on day one. I started looking at some of the videos that were on, that you had all the training videos, really nicely well organized into great sections. I went through all the videos and I'm like, this isn't too bad. Then we had James's team basically have us have on the books for consulting. So we opened up a consulting order with them to say, hey, if we need any help, we call you. When you spend a couple of hours talking to us, we want you to be paid. So we got that set up to make sure that, you know, we didn't wait around because they have all the other customers as well to deal with. So that was really the key. Not only that, they'd sent, I think they came on site 2 times to really take us through the course. Actually set some of the approaches that we're going to use because, you know, they know how to use their tool really best, and we kind of explained what we were facing. So they really kind of guided us into the best approaches and methods to use hypersizer and how to use it. There are a lot of functions in hypersizer, but I kind of stayed my lane and I just needed to get my job done, and you know, that was it. The main function for me was to make sure that we optimize this thing and get the substantiation report out of there. It's not something that I would have taken on had it not been for sort of James's team and the Collier software. Basically, looking at that, I've not seen that in any other software. Still to this date, I don't think you guys have any competition. There isn't anything that I've used that even comes close to composites. So it really was. I mean, it's an eye-opener for me. And I was with Altair for a very long time. So yeah, it really is. It's a great tool. So one of the things we did was, okay, we mapped these loads that were coming from GFAM onto a DFAM. We want to make sure that, hey, something didn't go wrong. So we kind of do a check on global check, displacement, stresses, strains, make sure they're all in the ballpark that we're expecting. We were expecting a little bit of a softer response, in which, you know, because of the detailed FEM model, and that's kind of what you see on the spider plot. So this was just a check. There was a number of other checks we made. I'm not going to go into all of those. There was also a lot of load cases that we reduced down to a handful just by looking at P1, P2 max strains across the load cases, just manual kind of filtering of loads. I know at that time there was a loads filtering inside of hypersizer, and I know there is one now for sure. But again, as I said, it was something that I wasn't used to, so I was just comfortable doing what we did. I think Bill was the main person that kind of reduced the load set for us. So this is a flow chart. Everyone probably follows this in some form of or fashion. This is just a pictorial to just show you how and the flow of the optimization. Rapid sizing is the key right here because within 20 minutes, this was run. We didn't have a mainframe cluster or any kind of. We just had one workstation, 20 core. That was our thing. 256 gigabytes of RAM, and had we done it in any other software like Altair's OptiStrut, I think that would have been one of our roadblocks that we might not be able to get optimizations turned around in quick enough time. This thing within 20 minutes gave me a result to say, hey, yes, you can change apply or no, add apply. These are the margins. So really, I think most of you are users of hypersizer, and it's just amazing. I don't think, if you just started using hypersizer, I don't think you understand how difficult it is if you don't use hypersizer to calculate these margins. You've got to go into your FEM model, you've got to extract loads. There's so much cutting and pasting and adding up, basically filling in equations, pulling data, because nothing is very seamless. You have to go from a OptiStrat OP2 file or an out file, get the results, put them into some formula you've created in Excel. There's a lot of, you're prone to errors. The best thing about a hypersizer was it just gave you the margin that you're looking for, and it actually pointed you into exactly which part needed the extra ply, or where you can take some plies out if the margins were high. Okay, let me go back, make sure. So the process was, we run DFEM we created DFEM in HyperMesh, run the static analysis, modal analysis in OptiStrat. Of course, we have the loop going back to OptiStrat to update stiffness matrix if needed. Typically, we didn't do that. We just sort of sized it for a while, and then we just did a couple of checks to just make sure that the loads didn't kind of shift somewhere else. And then we do a CAD update in CATIA. It's a bit kind of important, because by the time the designer puts all this information, there's things they can't do that they thought they could do. So you have to rerun. You have to make sure your model's up to date and is exactly as they're going to make it. So that's where we do the linear static analysis, just to make sure everything's all the margins check out. And then the reporting is really the key part. And I put a little clock there because it saved us at least 2 to 3 weeks not having to write the report. It's really that much time saving. As I said, we also did the inlet duct, and you can add another 150 pages for that as well. It's not 9,000 pages like the drone that we saw yesterday, but remember, this is a smaller part of it, which will go to Lockheed, and I'm sure they have more than 9,000. That makes the overall report for this. But yeah, very slick. I can't speak enough about how well the reporting was at that time. This was 4 or 5 years ago, so I'm sure it's at a different level now. I think somebody mentioned yesterday that not only you just get the margins, it gives you how it's derived. It gives you the basic equations and principles how the margins are derived. Not only that, you also have the spreadsheet, which has all the loads of all the elements. So how the loads were extracted from the DFEM, it's all there. If you needed to go and interrogate anything, you can go from your report straight to the element number, straight to the spreadsheet, and understand what the loads were. It's just a fantastic way of doing things. Here's just a small image of the front part of the nose cone and some of the zones, sizing zones we created. As you can see, so the blue area is where they had a removable cover. They wanted to get access to their data recorders and some instrumentation they had placed in that little front area. So they wanted that to be able to remove that. So that's a little cover at the front. The whole nose cone is basically made into two main pieces, because Swift didn't have an autoclave that was long enough, so we had to make it into 2 pieces. So these are some of the real challenges that you come across when somebody comes like this. And it was good that they said, yeah, you can make it however you want. They didn't have a desire to make it into 1 piece, or we could have made it into several pieces, but 2-piece main cone. So it had a top half, a left side and a right side that came together. So it's 4 pieces overall, but made into 2 main pieces. Main reason was our autoclave was just a little bit too short to make it all into 1 piece. 1 piece would have been preferable, but yeah, it ended up the way it is. So it had about 5 bulkheads all the way through, and composite laminate, cord composite. You can see the yellow borders. Those are the core ramps, and the salmon color are where the core is. Of course, you have the same thing on the underbelly, underskin as well. And both halves are coming together with fasteners all the way along, bonded and fastened. There's a boom that goes at the front where it kind of looks very sharp and pointy. That was the original design. That's where the boom was. But then they, just like all the other programs, they came back and they gave us like a 8-foot long boom to stick on front of that. So we had to redo the front bit because it was not made to carry any kind of any kind of loads, any kind of a huge moment arm. So we had to redo that. That little brown piece that's at the front, just an amazing challenge to even make that thing in composite in one piece. It was just unbelievable how challenging it is to make that into one piece and make it look really nice. Let me make sure. Yeah, so just like most of you guys, you kind of use smear laminates to get you in the ballpark, what percentages of plies to use, and then we go into discrete sizing after that for metallics and for the plies. We didn't have any draping tool, so some of the bulkheads are composite, laid up, and manually in HyperMesh we adjusted the normal the element orientations the best we could. I think you've seen a couple of these slides from previous presentations yesterday, just what comes out of Hypersizer. As I was mentioning, you can quickly look at the margin column and go straight to the one that has the closest to 0 and kind of home in and make sure that, what is that, and try to get a better understanding. Why is that happening? Is it a modeling issue? Is it or is it actually a real real issue that we needed to add plies or make it stiffer or weaker in some cases? So yeah, it zooms you right into the actual area. Not only that, it tells you which margin out of all the failure criteria we're aiming for, which one is not passing. So you could actually just decide to say, you know what, that's probably not realistic. It's okay maybe to have that to be a little bit lower. Our target was not to be at 0. We obviously wanted to leave a little bit of buffer, maybe 10%. So we wanted to try to be more than 0.1 in most cases. Some cases it was just, yeah. We also were able to quickly understand, like, okay, what does that mean? If I can get my margin down or up, how does that impact mass? And we can quickly do those studies really fast to say, okay, if I add 1 ply, what is that? And how is it affecting my, my overall margins, but what's happening to the mass? I did forget to mention that at the beginning, Gene Folsom, who's the chief engineer at Lockheed, when he came to us, said, hey, can you take 50 pounds out? We didn't really understand the structure or what it looked, whether that was possible or not. But after a while, we kind of got comfortable, like, yeah, this is doable. So next time we met, we asked him, hey, Gene, we'll be able to take some mass out, but you need to do something for us. And he said, okay, what's that? And we said, you got to get us all skunk polo shirts. So he said, okay, if you get 50 pounds out, we'll get you that. So just hold that thought. Again, this is this is part of the reporting now. So this is what's in the report and how all the loads are written up, how the margins are calculated. This is just a snippet of the report. This is not the actual report. But this is the kind of information that flows into the report. Now, I can't even imagine writing all that up by hand, going through every part of the whole nose cone. It would not have been an enjoyable thing to do. Joint analysis. So not only the laminates were sized for at the joints, but also the fasteners themselves. The little table on top is what comes out of Hypersizer, the BJSFM method. James was able to give us a couple of plugins at the time. There were plugins. I'm not sure if they're mainstream now, but they were plugins at the time. There was this. The other one that I forgot to mention at the beginning was the organization of the model inside of Hypersizer. That was done in Excel. And James gave us a plugin that would basically read in our Excel organization, and it would basically populate all of the components into their correct assemblies inside a Hypersizer. That was huge. That was like, especially if you're not used to the tool and you're not used to how to move things around, that was so good for us because I could just change, okay, I want to move that part into this assembly and just do it on the Excel. Rather than having going into Hypersizer. So that was huge for us. That was a lot of big time save there. So there was a few plugins. Also, the core ramp was a plugin at the time, I believe. Yeah, trying to do core ramps in traditional FEA. I wouldn't even know where to start. So just fantastic ways of calculating margins. There was a buckling requirement. Modal requirement, I should say, but we did the buckling checks and crippling checks on the whole structure of the nose. Where we did have low margins on crippling, we did go and like locally pad up the areas that needed just a little more stability. These are just some mode shapes, exaggerated, just to give a flavor for what the mode shapes are going to be like. At the very right-hand side of this nose cone, that attaches to a metallic bulkhead, which is part of the main fuse. And we're only allowed to have one row of fasteners. So that was the thing that kept us awake. It was like, why can't we have 2 rows of fasteners? And they didn't want 2 rows of fasteners. That was just one row. So that was probably the most worrying thing about this whole analysis for us is like, is that going to be good enough? And we're really close on a couple of those fasteners on margins. But that's what they wanted. And we did flag that, say, hey, just reduce the risk of not having this single row, but they just wanted to go with one row of fasteners. So just something that was, I guess, not worrying from a results perspective, but just worrying from an engineering perspective. Just nice to have 2 rows there. The dimensional stability was measured. So there was a 210 thou maximum deflection anywhere on the nose. Not the total tip nose, but any dimension on the nose. So they had to keep dimensional stability. And they also had a 48 thou what's called loft angle. So you can't have a 100 thou and then suddenly it rises up. So that slope is what they're worried about, that you couldn't have sudden shape changes like that. So that was our requirement, and that was one of the main reasons why we went to cord composite. It's just worked out really well. We did try out a lot of different options for core, height of the core, type of core. All that was run really fast in Hypersizer. I think all of you kind of do that on a daily basis. But these are just 2 of the dimensions that we're measuring all the way. So every 12 inches, they had a criteria. So every 12 inches, you couldn't be within 48 thou difference. So as you can see, it's well within that in both dimensions, the vertical plane and the lateral plane. Just a plot of margins on that nose fairing. Just something that is, I think somebody mentioned yesterday that chief engineers can look at this and kind of like understand, or loads people can understand what the part is doing. As you can see, most of the part isn't doing much. It's just where things are attaching to it. It's sort of lighting up. So on this is really important part of the reporting. When they go and manufacture this, those holes they have to drill, there's no guarantee those holes will be exactly the way they make them. And it's quite common for them to say, hey, Mahesh, I misdrilled this hole. I need to go and do this. What can we do? So we open this up, look at it. Hey, no worries, the margins are quite high in the area. Do whatever you need to do. But in other areas where margins are really tight, then now you got to figure out what is the countermeasure we need to do. So this kind of plot is so powerful even during the manufacturing stage, because it's not done yet, because analysis is done. Making it is another, a whole new thing, because there'll be things that as you're making it that will come into play that we can't even sort of predict when we're doing the analysis. We did do basically spring in analysis. So when these two halves are made, when it comes out of the autoclave, it sort of springs in a little bit. So we need to spring it back out. Put the bulkheads in. So when you close it, it loads up the bulkheads. So those loads are also considered preloading the bulkheads. It wasn't a lot, but we still included that in the reporting and the analysis. It was part of, because we needed to maintain the overall shape after it's made, not just sort of in its natural stance. I'll give a couple of minutes on this image. So there it is. We made that in record time. We had, as I said, about 6 to 8 weeks to do the analysis. The tools had to be cut in order to make our final time. This was all during COVID. And March was when we delivered this nose to Lockheed. And so, yeah, it's just, when we had it at our work, yeah, people were just staring at it for the longest time. And I've heard Gene tell me that the first thing VPs walk in at Lockheed and say, wow, look at that nose, who made that? That's the first thing they say. But then they forget who it was Swift, obviously. They want to hear Lockheed, but so yeah, it's just it's one of those projects that it's just pride of America, right? This is the thing that kind of keeps us in the tech, and so good that NASA actually started this project, and they're trying to do this. Just for me personally, it's a great pride to even be involved in this. Just happened to come on my table, land on my desk. Yeah, so you can see the fuse there, the 214 bulkhead, and not only there's another picture, but not only we had to deliver the nose, we had to create a system to carry the nose into a cradle. So that was also built, a little cradle to give it to them so they can move it around. And that's not the cradle there. There's another picture I'll show you later. That's their equipment. So this is at Lockheed, getting ready for mating to the fuselage. So we made that, sent it to them. Of course, they went silent. Nothing. Everything's fine. Not hearing from them for a few months. They came back. They were doing some testing in Texas. So they took this out to Texas at their main facility. And so they were doing some static testing. Of course, they can't take it to ultimate, but they were just doing some proof testing. Main reason for the test was to calibrate the models to make sure that the models were predicting the right deflections and the right strains. So they did that. They had a bunch of strain gauges and actuators, and they pushed it and pulled it in both directions. And they came back with some results and said, "Hey, we have some data for you." They also had our models, so we gave all the GFEM, DFEM, everything to them, hypersizer databases, everything. They also had that. They had the analysts working during this testing. They did give us some data back, a limited set, and said, "Hey, here's some, because I asked for it. I said, hey, I really want to know how it was." So they did give some data back to us, so we could actually do a little bit of correlation. So this is a correlation of that, of the data they provided. I'm not sure if we got really lucky with the strain gauges, because strain gauges are, as somebody was saying yesterday, are just, you could be 200% off in the wrong direction. So very happy with that at least we're in the right ballpark. For me, the main one is really the deflection test, as a more of a macro test, global test, where if you get the overall stiffness of the structure right, the rest of the model is good. So that's really the deflection, the tip test. You'll see a couple of dots in the green on the strain data. So those are a little bit conservative. It's not that we left weight on the airplane. We had to stop. We could have continued this for another 6 months and got maybe more weight out, but we had a timeline. We had to stop. So, yeah, good correlation. And so in conclusion, so there it is. And there's the dolly we made for the nose as well. And there's the full aircraft right there. Yeah, it's just amazing to just see it up close. I'll just summarize and conclude a little bit. So without really hypersizer, I think we would have taken much longer to do the same thing, maybe months more. And as I mentioned, it's just a tool on its own. And it would not have been possible had it not been for the support of these guys. And that's the other thing of a software. Software can be very capable. If you have really bad support, nobody will be able to use it. All the great functions will be hidden, and nobody will be able to know how to use those. These guys are at heart engineers, and they know how to help companies in a variety of ways. They don't know the product because they don't own the product, but they know how to achieve the end goal and how to get their software into the hands of people like us. So really, thank you for the Collier group to make this a success for Swift and us. In the end, we got our weight down. Any guesses what the weight was? So we started north of 400 pounds. What do you think we ended up at? Not bad. 305. So they were ecstatic about that. And it was, yeah. And as I said, there's probably some more mass to be taken out of there, but we didn't have the time to do that. So I'm sure we can get it even lighter, especially with all the new features we have. We didn't get into all of the DOEs that we could do in the software. But yeah, it was amazing. And so Gene came in one day without polo shirts with the skunks. So thank you for that. And that was the end of my presentation. So yeah, thanks. Yeah, any questions? And Bill, I might need your help to answer some of these questions as well.
For the testing, were you guys given any test cases to potentially, I guess, do any analysis for, or was all the testing, all that handled by Lockheed?
Yeah, for the nose cone, it's all Lockheed. They didn't specify anything even for us to go and test. But for the inlet duct, we had to build a small test pieces. There was a T-flange that was bonded onto the duct. And yeah, so we did do some of our own testing that was not required by Lockheed, but we just wanted to make sure our model and modeling methods were correct. So we did do some testing for the duct, but not for the nose cone.
What was the thermal environment like, and what material system did you use?
Yeah, so thermal was a challenge. It was hard to get any kind of thermal loads out of Lockheed for a long time because they're based out of a different division than the guys who gave us the project, so it was a little bit hard to get the loads out. It's around 200 F at the front during cruise, so it does play quite a bit of role in just expansion, especially when we have aluminum and composites going together a little bit. So yeah, it's IM7.
Were you able to size everything with the internal loads in the model, or do you have to apply any pressures locally with the software?
So they gave us the internal loads. They also gave us the aerodynamic loads, and so we mapped those onto our DFEM.
Did you use that in hypersizer, or did you process those internal loads in the FEM?
In the FEM, yeah, in the FEM.
Thanks.
With the cord pieces, how did you deal with the curvature? Was it like a flex core or machined?
Yeah, most of the nose cone is basically two-dimensional curvature. So that was, yeah, that sort of, we did look at, in some areas we did have to use flex core because it did curve quite a bit. In a lot of the areas we just use just the regular core. Yeah, it was challenging because, as you all know, depending on which core you choose, your mass can be drastically affected as well. So there was the balancing going on which core and how much it weighed and what the benefits were for that. So we did look at multiple different types of core options. A lot of the materials had to be Lockheed because they needed to be in their database. They didn't need to go and recertify the material. So we had to pick whatever the kind of handful of materials they wanted us to use. So we're kind of a little bit restricted on the material itself and the system. Yeah. Okay, great. Thank you very much.